Welcome to the lecture today, students. So in this lecture we're going to learn about phylogenetics. We're going to explore how it is that we can determine the relationships of organisms. And to do this we're going to start with an analogy. So I want you to imagine that there is a forest, and in this forest there's a start line and a finish line. And across the start and finish line there is a pathway, but we can't see the pathway because it's covered up with the trees. But what we have is a way of determining what the pathway is by using runners. So we can send runners through the forest, and they can go through the pathway. Now the pathway, there are some things that we need to learn about the pathway here. First of all, in this pathway there is only one starting gate. So we have over here our one starting gate, and all of our runners must run through that pathway. And we're going to do 7 different runners. We're going to call each of our runners A, B, C, D, E, F, and G. Now remember, there's this pathway that we know that exists in this forest, and this pathway has stamping stations along the pathway. So you can imagine, there's someone that's sitting right in the middle of this running path, and they've got a stamp, and every time a runner runs by them, they put a stamp on their card. Okay, so we're going to send these runners into the forest. They all start through a starting gate, one single pathway, and we know that this pathway diverges throughout the forest, and it always is bifurcating. In other words, it always divides into 2. Okay, and as the runners run along through these, what are represented by these squares, those are our stamping stations, they have a little card, and so as they run along through that stamping station, then they get a stamp on their card. And then they go further, and then they have to make a decision. The runners either have to go right or left along these branching points. And as they go through a branching point, they'll run a little bit more, and then they'll come across another stamping station, and they'll get their card stamped, right? So they do that, and all the runners go through this, and again, they go at different times, but they're all going through, and they're deciding to either go right or left on each of these bifurcations, each of these splittings. And we know that all of the runners also come out of their own separate pathway at the very end in the finish line. Okay, so they all start through the same one, but they end up in their own distinct pathway that comes through the finish line at the end of the forest. And they all have with them, they're all carrying their little cards. Okay, so given just that evidence, our job is to use the cards to determine what the pathway is in the forest that we can't see. Okay, so here are their cards. We have runner A, who ended up having a star, a circle, a V, an X, a triangle, and a heart, right? And runner B had this set of stamps, and runner C had this set of stamps, and so forth. So the question is, from just the evidence of the stamps, can you determine what the pathway was in the forest? Well, one way that you need to do this is to start looking for similarities across all of the runners, right? Similar stamps. And I don't know if you noticed this, but all of the runners have the X stamp. So where would that go? You can already start to think, where might that be, in that pathway in the forest race, and all of these pathways in the forest. And if we look a little further, we might say, what's another very common stamp that we see here? And maybe you saw the triangle, right? Where now we have all of the runners except runner G got a triangle stamp. So maybe that starts to give you an idea. So as we come back to the forest, then we can now start to maybe put down some of these details. So we had that starting gate that the runners went through, and all of them had an X stamp. So clearly the first stamping station that all of them ran through was the stamping station. This first stamping station, we're going to call that stamping station X. And then we know that the majority of them, except for runner G, got a triangle. So maybe, we can imagine our first bifurcation, and coming down along this way are all of the runners except for runner G, and runner G went up this way, right? So we send all of our runners through this race course, and they all finish, right? That's what we need to do, and we need to figure out what is the race course, what's all of the pathways in between. So I'm going to bring the cards down here so that we can kind of refer back to them. And we see, to start to finish the race, we can look at runner G. We know that it has an X, a square, and a moon. Well, no one else has a square or a moon. There's not one. They have a rectangle, but not a square, right? So we can say, well, runner G, after going through this initial stamping station, went through gate that had the rectangle and got the square stamp, went through the stamping station that had the moon and got the moon stamp, and then ran all the way, and there were no more stamping stations along this particular pathway, and runner G came out of the forest with those 3 stamps, right? And we can come down along the other pathway, and we can notice that also all of the rest of the runners have a star. Star, 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 star. So they all also went through a star. But then we start to see some differences. We see a branching point now where runner F, for example, has these 4 lines, and no one else has the 4 lines, but it has the X, star, and triangle. So runner F branched off up here, went through the 4-line stamping station and to the end. And we can see that runners A and D, right, came through a stamping station of a circle. Actually, the rest of them went through a stamping station with a circle, and runners A and D then branched off after that and went through a stamping station with a V. And then they went a little bit further, and there was another branching event. And then runner A went through a heart, got a heart stamp, and finished the race. And runner D just went and finished the race without the heart. And at this branching point, we can follow it to where the rectangle is at, and we can see that runners B and runners C and runners E have that rectangle, so they're still trying to finish the race here. And we can finally say, well, C had nothing else besides the rectangle, so it just ran to the end. But runners B and E both got hashtags, so they get the hashtag. Runner B doesn't get anything else and runs to the end. And then runner E goes through 2 more stamping stations, a check mark and this kind of arch. And so runner E has to go through those. So the point is, by using the evidence that was found on the cards of these runners, we were able to reconstruct what the race course looked like. Now, I've done this before with students, and students can actually come up with different race courses. So look at these 3 race courses. Are they all exactly drawn the same? Clearly not, right? But if you look closely, they all have the same ultimate relationships, because G is off by itself and it only went through the 3 stamping stations on all 3 trees. It didn't matter how it's drawn there. And you can see that, for example, B and E are always sharing that most recent branching event right after the hashtag in all of the trees, B and E. So even though they're not laid out all exactly the same, the relationships of each of the runners and the stamping stations which they went through are exactly the same. Okay? Now this is really important, because as we think about this with organisms, when we talk about organisms, we can now use the same approach to reconstruct the evolutionary history, or the phylogeny, of the organisms. So if I take now these 7 organisms, a gecko, a human, a cow, a crocodile, a pigeon, a trout, and a salamander, and I look for characteristics that are similar and different among these organisms. So for example, if we look at the crocodile, we can talk about characteristics like an amniotic egg, a vertebral column, 4 limbs, a diapsid skull, an antorbital fenestra, which is this extra hole in the skull and the lung. So I could look at these characteristics and compare them to the other organisms and decide which organisms share or don't share these characteristics. Or maybe they have, some type of characteristics that's completely unique to them as well. And just as we did with the race cards, with the runners, we can do the same thing for these organisms, and we can look at these and say, oh, well, they all share vertebral column. 1, 2, 3, 4, 5, 6, 7. All of them have vertebral column. So that is the same thing as saying the X. All of them had the stamping station of the X. So if we come back to our map here, and we can replace essentially if we do the same logic of everyone had an X, and so therefore the X must have been the first stamping station, and then after that there were branching events, we can do the same thing with this, and we can say, okay, all of these organisms came through a pathway that initially had an event where a vertebral column was evolved. Then there was some splitting that occurred, right? So speciations, where you had this population of organisms that split into two different populations and started to evolve along their own pathway. Along one pathway, a swim bladder was evolved. And you went a little bit further and ray fins were evolved, and that led to things like fish, or like our trout here. If you come, though, down a different pathway, four limbs were evolved, and lungs were evolved. And this led to all the rest of the organisms. And then you had a splitting event where you had a particular type of teeth that were evolved, and that led to salamanders. You had the egg that was evolved, and then that led to another splitting event eventually that led to a certain type of skull, or to hair. And the hair led to a splitting event eventually where you had humans that evolved and lost most of their hair, or rumen in cows, and so forth. So just as we can use evidence of the stamping of these runners in the race, we can use morphological and genetic characteristics to help us infer what the evolutionary relationships are of these organisms. So as we look at this, we can clearly say the human and the cow share a more recent common ancestor, which is indicated by the branching event. Okay, so common ancestors are branching events or splitting points in the tree. Those are what we call common ancestors. And the stamping stations are equivalent to evolutionary innovations. At the genetic level, this could be a mutation, or at the morphological level, it could be a bunch of mutations that eventually lead to something like hair, right? And it's also important to realize that all of these organisms, because they are currently alive, are all equally evolved. They're all winners of the race, in a sense, right? We never would say that a gecko is more evolved than a trout, as we would never say a human is more evolved than a pigeon. We are all equally evolved. Hi, I'm back with a new shirt on. I wanted to make just a few more points about this phylogeny and this process that we did using the race analogy. So first of all, that I want you to realize that these characters that we now used to help us build this phylogeny is only a subset of the potential possible characters that could be out there, right? In the universe of characters. Across these organisms, there are hundreds and hundreds, perhaps, of morphological characters that have been well studied that we could use to help us build this phylogeny. But in addition to that, we now have all of the genetic characters, right? All of the DNA. In fact, almost all of these organisms here, we've already sequenced their entire genome. So we could use those genetic characters. We could also use behavior or distribution or a bunch of other different characters to reconstruct these trees. And the more evidence that we have, the more confidence we can have that we've actually got the relationships right, that we got the right tree. So that's the first thing. Next thing I want to point out is that just because some of these branches happen to look particularly long or some of them look particularly short, that does not necessarily mean more or less evolution. This is just a representation, again, of the relationships of these organisms, or in other words, it's just the race course. So don't get caught up on length of branches. Also, don't get caught up on the number of nodes that a particular organism went through, or a number of branching events, right? Branching events or nodes or common ancestors. We should not count the number of branching points and say, oh, that organism then has gone through more evolution. We don't count the number of branching divisions either. We also shouldn't count the number of characters. Just because one, the pigeon, for example, here had the most stamps, it's incorrect to say that the pigeon then, is more evolved, or if something has less stamps, less characters, then it is less evolved. The other thing that's interesting to point out is that in some of the cases, for example, the swim bladder and the ray fins here, they both occurred along the branch leading to the trout. Now, I've arbitrarily placed swim bladder early and ray fins later. But these could easily be switched, and they could be more further toward the trout, or they could be more further down towards the branching event after the vertebral column. So where these characters are is not exact either. We just know that they occurred between the, either two branching points or a branching point and the modern day organism, or the terminal end of that branch. The other thing is that all of these characters, for example, right here, are homologous characters because they are shared by the ancestors, and they were present in the common ancestor of these organisms. But if we were to put something like wings, and we happen to have bats and insects and birds on this tree, we have a pigeon, but if we also had bats, they would be over here by the mammals with the cow and the humans. And if we had insects, that they don't even have a vertebral column, so they would be clear outside of all of this. And if you had to put just wings, do organisms have wings, you would have to map that character 3 different times. You'd have to have 3 different stamping stations that had similar stamps, all showing wings. But if we look at the details of that character, we realize that each of those wings are different in their origination. They had different independent events in which they were evolved along the evolutionary tree. So you'd have to have 3 different stamping stations. So that is an example of a character that would not be homologous, but an example of a character that would be analogous or non-homologous, or sometimes we refer to this as convergent evolution. And the last point I want to make is we did not have to be present when the race was being run to figure out what the race course was. All we had to do was have the stamping cards of each of the runners. Likewise, we do not have to be present to watch evolution happen, to know that evolution happened and that it happened in a particular way, or at least to be very confident about the way in which it happened. And again, we just use the overwhelming evidence of characters and genetic characters to reconstruct the evolutionary history, to reconstruct that tree. And we can usually be very confident in the trees that we reconstruct. Not always. Sometimes we have a lack in our knowledge of relationships, but in many cases we have a very strong knowledge of the relationships of organisms. So anyway, so that's your first primer now on phylogenetics and reconstructing evolutionary trees using the Clade race, and then showing you how that compares to real world organisms.